Thank you very much for the opportunity to present today. Um, in order for a democracy to be successful, I think it's been long recognized that citizens need to be able to read. And as a result, governments and democracies have invested in upskilling to make sure that people have the necessary literacy skills. I think the situation we face today requires that governments expand the notion of literacy to include the ability to interact with data, the ability to interact with information on the internet in order to have citizens effectively engage in shared governance. We need an expanded collection of skills. And so what I want to describe today is a pathway to try to make it a human right to participate in science, a human right to participate in data-intensive, computational, narrative storytelling. It's not that everyone will want to do it, but everyone should be able to do it. Just like everyone can use the letter K without having to pay a tax, everyone should be able to use some aspects of the computational cloud to do some things to help them understand their relationship to the universe. And so I'll describe that by sharing my screen and going through some slides. Once again, thanks for the opportunity to present here today. So I hope that you are all seeing my slides that should say Cloud Streaming Science. Hello,
Absolutely.
I'm James Colliander, and I'll be talking today about a not-for-profit that I helped to co-found called the International Interactive Computing Collaboration, or 2i2c.org. So what is science? Science is a systematic enterprise that builds and organizes human understanding of the universe with testable explanations and predictions. It's humans that are going to understand the universe, and the way that we do it is through this process of experimentation and validation and collaboration and conversation. And it's a grand enterprise. We have whole structures like universities and granting agencies and laboratories built to advance this enterprise of science. And this is kind of trite, but the idea is that science improves our understanding of the universe. And through that, we have an opportunity to improve our society. I think although it was controversial a few years ago, vaccines are really useful. They help keep everyone safer and live longer without pain. But I also think that this statement, which looks good, but it's also a little bit trite because implicit in it are questions of values and power. Inventions like nuclear weapons and inventions like artificial general intelligence have potential risks depending on who controls the impact that these scientific advances have. So it's not just advances in understanding. I think it's also the way that we as humans evolve with our understanding of each other while we learn more about the universe. And so we have to look not just at science as a be-all, end-all good that is good no matter what, because knowledge is good no matter what. I think we have to look at knowledge carefully as it advances and understand who is it that is understanding and what are they doing with it, and how can we make sure that everyone has access to that knowledge, or is it restricted to a small group of people? So there's a lot of values and power around science that we also have to think through. So the North Star of science is we as humans understand the universe better, and the universe might be fusion energy in this context, or it might be trying to understand social behavior in a new way in social science, could be understanding how to use Monte Carlo methods in chemistry or something. But we as a group of humans begin to understand things more deeply, or we might teach others to understand that which we've learned. And the method, the fundamental activity of science, is humans talking to one another. Sometimes we do it in teacher-student relationships. Sometimes we do it as collaborator to collaborator. but the fundamental activity of science is the exchange of information. And right now, science today is really a dialogue between people and data using computers. And this magic triangle of data coming out of instruments, being analyzed on computers, rendered on laptops or rendered on monitors, and then interactively understanding what we think we know about the universe is the magic triangle of producing new science. And one way that we advance science is by students or collaborators coming into this triangle and working with us and trying to understand things. And then they matriculate off as trainees or experts. And so we grow a larger collection of people that understand the universe through this talent pipeline. Another is that we make discoveries. So insights from experiments or insights from the literature become data that we process together, working with computers and working with each other. And we produce scientific articles or data products or ways to make better decisions. And so in this way, we have a pipeline that advances knowledge. So the most important component in this whole enterprise are people. And I saw these axioms that Ardila first wrote down. They were first written down in the context of mathematics, and I've generalized them here to think about the scope of being science. When I first looked at them, my reaction was like, yeah, well, this is obvious. But it's maybe obvious to me because of the relative position of power and privilege that I've had. I think there are a lot of people in the world that look upon these and say, yeah, that may be true, but I don't have the library card that allows me to get access to the book that I wanted to read. Or I don't have access to be able to put my eyeball on top of the eyepiece to look through the telescope. So although everyone may have this potential, the way that access to science, the way that participation in science has been made available is very much based on a gradient. There are certain people that have better access than others, but these axioms help us to think about the potential for expanding the human understanding of the universe could really grow quite a bit if we just made sure that people that are presently excluded for either power-based reasons or circumstantial reasons, if everyone could participate more, then we will expand the goals of science. So this fundamental activity of science is the exchange of information in order to improve the human understanding of the universe. How have we exchanged information for science? Well, for about 10 to the 5 years we've talked, we've told stories. For about 10 to the 3 years, we've traded paper. And for about 10 to the 2 years, we've talked through the telephone or the telegraph. And for just on the order of 10 to the 1 years, we've had a different system of cloud communication, and we're just learning, I think, how to use this ubiquity, this omnipresence of the cloud to change the way that we carry out science. And I call upon the audience here, people that know Python, that work in the Department of Energy's labs, to recognize that this is an epoch-changing moment for our generation. We have the opportunity to change the way that people understand the universe and influence it, to expand the audience and to improve people's participation in the discovery process. This cloud era brings remarkable opportunities to open up science. And 2023 was christened by the White House and by UNESCO and others as the year of open science. And there's been a real call to change the power structures and the systems for participation in science. And I think the cloud presents the technology for us to follow through on that call to action. So how is it that technology and maybe some changes in social structures can improve our understanding of the universe? We want to improve the talent pipeline by getting more people trained up better and more people having access to that training. And we want to get more people capable of making the deepest and most powerful discoveries and then enable them with the ability to share those discoveries. We're in a bit of a skeuomorphic moment right now in the way that we communicate in science. We use terms like email to evoke what used to be called just mail, and preprints to evoke what used to just be called printed. Articles and papers are now delivered to us digitally in formats that are really kind of digital replicas of prior ways of packaging up a bundle of ideas. An article is now delivered to you in a PDF format as opposed to in a photocopy or in a journal volume. But we're really stacking up the ideas of a scientific story using the same sorts of structures that were defined hundreds of years ago in the paper-based era. But we're now at a transformational moment where we might be able to use these cloud-based systems to communicate scientific ideas in new ways that allow more participation and deeper interaction, faster reproduction, better validity of all of our advances. And so we have an opportunity to transform the way that science operates. Imagine the future from 1948. This was quite a remarkable summer. So this image might be from the most influential paper of the past 100 years. This is from Claude Shannon's paper in which he described information theory. And in this paper, the quantification of information using the concept of a bit first appears. And it's kind of an abstract way that information is transmitted from a sender to a receiver. A few weeks prior to the submission of this article for publication, this patent was submitted, which was for the first transistor. And this was all in basically the same hallway at Bell Labs. Now imagine in 1948, knowing that you had just established the digital atom, the atom for making signal processing scalable across an entire planet, and that you'll build on this vision of Theodore Vail, the CEO of AT&T in the 1906 timeframe, that we might be able to teleconnect every pair of human beings. That wasn't the case in 1948, but with the invention of the transistor and this quantification of information, those individuals saw a future. They saw deep into the 75 years that we are now living in. And just imagine what it was like to look at that future from that time of discovery. And now put yourself back in the present and imagine 75 years from now, or maybe just imagine 10 years from now. How can we build a better future using all of the power of Python, the cloud, interactive computing, and the connections of all of these scientific instruments to the eyeballs of everyone across the world? I think we're just scratching the surface. So imagine science in this cloud streaming era, and let's try to build it. Let's try to build it so that it's awesome. What's the future? What's that future that you imagine? Does Microsoft own science? Does Google own science? Do we have to pay a tax every time we make a Python call? Or can we imagine a human right to participate in science that's enabled through a system of digital public goods that enables everybody to participate in data-intensive computational narrative sharing? I want to build that alternative future with a human right to participate, and I'll tell you about a little background of my progress together with many others that have contributed towards trying to enable that future. So here's a timeline of some foundational work in open source and in the cloud. So back in 2006, S3 launched. Amazon Cloud was a little bit earlier than that. Microsoft Azure launched in 2010. The IPython notebook was launched just at the end of 2010. Shortly thereafter, RStudio. Google Cloud came on board in January of 2012. The first AWS reInvent conference took place in 2013. Kubernetes, a way to scale cloudy services, took place thereafter. And then IPython was generalized to include other languages with the launch of Project Jupyter. Shortly thereafter, Project Jupyter was created Jupyter Hub. There was a blog post that I'll mention by Jessica Hamrick that was really influential to me. Binder, a democratized way to use the cloud to access computational tools adjacent to a computational narrative, was launched in late 2015. Pangeo, a transformational earth science project, was launched, and Jupyter Book also came along. One of the things that I did around that time was start an education startup that began to help me to see the power of the cloud in delivering systems of collaboration to large audiences. And I took a new job as the director of the Pacific Institute for the Mathematical Sciences. And I started working with this gentleman, Ian Allison. And we wondered, after seeing this blog post from Jessica Hamrick, we wondered maybe we could make Jupyter Hub available across all the universities in Canada with a cloud deployment strategy. And we were inspired by this democratization of education and data science launched by the University of California at Berkeley. And we took great inspiration from this Earth system big data geoscience community platform called Pangeo. And what we ended up building was a timeline that led to the creation of a Jupyter Hub service called Syzygy. And this isn't rendering well, so I'm just going to skip it. So Syzygy now is delivering Jupyter Hub to many universities across Canada, 25 universities with an audience of about 75,000 users historically. And we showed that a single engineer with the power of the cloud and the available open source tools could deliver interactive computing as a service to a national scale audience. Around that time, I also helped to bring into creation a Jupyter-backed open education resources not-for-profit that delivered curriculum using interactive computing to students and teachers in grades 5 to 12. And these experiences led me to join forces with some of the founders of this open source ecosystem to create 2I2C. Callysto and Syzygy, while successful, were also kind of impending catastrophes because we did not have a proper business model or service agreement or sustainability strategy to make sure that these tools were properly backed up and made available more generally. And so 2I2C aims to be this kind of digital public goods provider as a not-for-profit that can sustainably deliver interactive computing to large audiences of researchers, instructors, students, and maybe more ambitiously to citizens. So with this remarkable team of co-founders, we launched 2I2C about 3 years ago. And our vision is for a global network of community hubs for interactive learning and discovery. And we want these hubs to kind of become a digital home or a digital village in which these folks can create and share knowledge between and among these different networks, all connected through the cloud. And we do so by offering some scaffolding that can be customized based on the particular audience's toolchain needs and the particular audience's data needs. Some data may need to be locked down and very secure. Other data might be publicly available. And when there's an idea that makes advances in these tooling delivery systems, say in the climate community, that idea might propagate through this open source ecosystem to become shared and used in a sociology classroom, and then other ideas may propagate over to neuroscience. This whole ecosystem is designed so that when someone comes up with an idea, that idea, maybe from a scientist, can be shared with the open source community that works on those ideas. And this idea for a new tool might get built into something that is actually deployed. And then this ecosystem of science and software development, information exchange, improves the tooling and enables more science. We've now grown to a network that serves more than 80 communities with more than 6,000 monthly users. We've also contributed more than 2,000 upstream pull requests to the upstream projects that we rely upon. And we have ongoing collaborations with a collection of entities such as NASA, Howard Hughes Medical Institute, and others. Some examples of the services that we run. We run services for the United States Greenhouse Gas Center, which is using Jupyter and related tools together with data from NOAA and from NASA to understand the federal government relationship to greenhouse gas emission and to monitor greenhouse gases. This goes beyond the requirements of the Paris Agreement and is quite a striking project. We've also done some really interesting work with a community that's studying the cryosphere called CryoCloud. And we have a list of running hubs that's available off of our site that shows where all of these communities are looking at things. Maybe the last thing I'll show is we also have a page that you might find 2i2c.org/KPIs, and it shows you a little bit of our global usage. This shows the hubs and active monthly users. It also shows the geographical distribution. Shows you some of the hubs. Well, with that, I'll pause.